So the Lewis model is a drastic oversimplification. These two atoms that are sharing electrons are things that are shared, always shared equally. Did you ever go on vacation as a kid and you had to sleep in a double bed with your sibling, right? And somebody ends up with all the blankets and the other person ends up with no blankets, right? Somehow it's always like that. Because you didn't share equally. Well, these shared electrons aren't always shared equally either. So here we're looking at a covalent bond between hydrogen and fluorine. They form a bond, so we have a shared pair of electrons here, but this cloud, this colored thing here, is representing the electron density. The electrons spend more time around fluorine than they do around hydrogen. So their orbitals are kind of lopsided, right? So that makes this end of the molecule somewhat negative and this end somewhat positive. It's not that the electron has been transferred. There's not a +1 and a -1 charge, but there's like a partial charge. And we can indicate that with this lowercase Greek delta. It's a partial positive charge on that end, partial negative charge on this end. So all of these molecules have one end that's a little positive, one end that's a little negative. If we apply a voltage to these metal plates and make this one negative and that one positive, these guys are all going to line up like little compass arrows. And the positive end will point towards the negative plate, and the negative end will point towards the positive plate because of the attraction between opposite electrical charges. So my analogy for this is little boys, they're neighbors, and they're playing with each other. And so one electron lives at the fluorine house and one lives at the hydrogen house, and they're going to play together. And so sometimes they'll play around in fluorine's house or yard, and sometimes they'll play at hydrogen's house or yard, right? So let me tell you about these houses. So fluorine has this big screen TV. They've got all the cable channels. They've got all the game systems. They've got a trampoline and a swimming pool with a diving board and a slide, right? They've got a soda fountain in the kitchen. If you're hungry, Mom will order pizza to be delivered just anytime you want. Cool place for little boys, right? I had little boys. Bunch of them. The other one, hydrogen's house, well, they've got an old black and white TV. It's like, didn't know that those could still work, but apparently this is vintage or something. Anyway, and they've got a VCR with some old Thomas the Tank Engine tapes. If you're thirsty, you can go get a glass of tap water. They don't even have a refrigerator water dispenser thing or ice cubes. You just drink, tap water straight out of the tap. And you might be able to find some saltine crackers or something in the cupboard if you're really hungry. No pool, no play set in the backyard, nothing, just maybe some grass. Okay, so where are those two boys going to spend more of their time? They're going to go over to Fluorine's house. Why? It's more attractive, right? It's more attractive to them. It's more fun. Fluorine is more attractive to electrons than hydrogen is. And there's another way to show, so we can say, this is the negative end, and this is the positive end. And another way is to, there's an arrow that points to the negative end, and this has a little plus. And I think of this as being, somebody comes over and wants to know where the two boys are playing, and Dad's out in the yard, mowing the lawn or something. They're like, where are the boys? He's pointing to where they are, right? Because they're over there. They're going to be over here. Okay? So the arrow points to the more electronegative, use that word too soon, the more attractive one, and then this plus is at the plus end. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. So basically, how cool is that house for little boys to play in? How attractive is that atom for electrons? There is an inverse relation to atomic size, but really the best trend to remember is fluorine is the most electronegative. So this is showing the periodic table, and how tall each of these is related to the electronegativity. So fluorine has the highest electronegativity. It's on a scale of 0 to 4. So fluorine is the highest. There's something missing from this periodic table. It's the noble gases, right? The noble gases make almost no covalent bonds. So if we're never going to be doing anything with them, why put them on the chart? Because they mess it up. We don't want them on there. It messes up the whole chart. So we just leave those guys off. So fluorine is the highest. And the trend goes, if you're going away from, pushed something. If you're going away from fluorine, you're getting less electronegative. If you're going towards fluorine, you're getting more electronegative. So these numbers you might need to use in a homework problem, possibly a worksheet problem, but you'll never have to do those on an exam. You don't memorize those. It's just fluorine is the most electronegative, and so you should be able to compare two elements and say this one's more electronegative than that one, just based on their position in the periodic table. If we look here, nitrogen and chlorine are both 3.0. They have the same electronegativity. So there are some things like that. Sulfur and carbon are the same. We don't need to have that level of detail. Electronegativity is an important concept. The lattice energy trends, you try to remember them, but it's not a big deal. Electronegativity is a big deal. You'll need it in Chem 1B, and you'll use it a lot in OCHEM, because they care about, well, which is more electronegative than the other. We need to be able to predict that. And we don't need to use the actual values, we just use position on the periodic table. So we should be able to say that, yeah, nitrogen's more electronegative than carbon. So this also is a typical type of exam question. Arrange the elements in order of decreasing electronegativity. And it's these guys. So first of all, find them on the periodic table. There's phosphorus and nitrogen and our friend Al and sodium. This is how multiple choice would do it. I recommend not looking at those. Put these in order and then go find the one that matches. They just all start to swim after a while. Just don't even look at those. So we know that fluorine is the most electronegative. Which of these elements is closest on the periodic table to fluorine? Nitrogen. So that means nitrogen is the most electronegative. This is asking for decreasing, meaning start with the biggest and go to the smallest. So nitrogen is the most electronegative. Okay, which one is next closest? Phosphorus. And then aluminum. And then sodium. Just compare how far are they from fluorine. And then we find the one that matches, and it's this one. Okay? Questions? So we just started talking about covalent bonds and how they don't always share their electrons equally. Well, there's a sort of a continuum here of sharing perfectly equally and not sharing equally to such a degree the electrons actually get transferred from one to the other. We're not even sharing anymore, right? and then in between where there's unequal sharing. And so we look at how polar a bond is by looking at the difference in electronegativity. So the difference in En for electronegativity, because it's got way too many letters, the difference in electronegativity. So there's three categories here. We have the nonpolar covalent bond, polar covalent bond, and ionic bond. How do we decide where the line is between them? Well, it's really arbitrary. So they've decided that it's here. So a difference of 0.4 or less, we're going to call that a nonpolar covalent bond. We're going to say, well, good enough, they're sharing equally. If the difference is 2.0 or greater, we're going to say that's an ionic bond, the electrons are transferred. And then in between, we've got unequal sharing, and so we'll have this polar covalent bond with a partial negative charge on one end and a partial positive charge on the other end. And this scale here with its divisions, you might need that on homework or something, but not on an exam. They measure how polar a bond is using something called a dipole moment, and we're going to talk about it on this slide, and then we're never going to mention it again. And so that dipole moment occurs anytime you have a separation between opposite charges. So the dipole moment is equal to the charge magnitude times the distance between them, and the unit is the debye, which is this many coulomb meters. We could also look at percent ionic character, the ratio of the actual dipole moment to the dipole moment it would have if it transferred the electron. So as it turns out, no bond is 100% ionic. So when we have an ionic compound, it's not actually a complete transfer. Well, this is kind of messy. I give you permission to think of it as a complete transfer. Okay, we can still think of it that way as long as we know that it doesn't really do that. So here, looking at percent ionic character, when we see these guys up here, they all have more than 50% ionic character. All of these are metals and nonmetals, which we learned were ionic compounds. Down here with low percent ionic character, these are nonmetals with nonmetals. And there's this guy in here, HF, which we always use as an example for polar covalent bonds. That's like the most extreme. This is the most polar covalent bond, but it's still under 50% ionic character, so it's still considered a covalent bond. Okay, so this is something we should be able to do. Look at a bond between two elements and identify, is this an ionic bond, a nonpolar covalent bond, or a polar covalent bond? And so I'm just going to show you my little thing for this. So ionic bond. Okay, that's when you have a metal and a nonmetal. That's the same thing we learned back in like chapter 3 or something, right? Metal, nonmetal, ionic, done. Okay? And then we have the covalent bonds. So nonpolar, same two elements. Well, same two atoms, I should say. So it's like, carbon and carbon, or nitrogen and nitrogen. Those have to have the same electronegativity, right? Because they're the same. So that's going to be nonpolar. There's one extra thing I want you to remember, and that is if you have carbon and hydrogen bonded, that is also considered nonpolar. The difference for this one is 0.4, which is right on the line, but the carbon-hydrogen bond is considered a nonpolar covalent bond. And this is an important one because it's just so common in OChem, right? Carbon-hydrogen bonds are everywhere, and we just need to know that those are nonpolar. So what about the polar covalent bonds? Two nonmetals. Two different nonmetals. Is this simplified scheme always going to work? No, it won't. I won't ask you questions where it doesn't work on an exam. Because we just looked at, there was some like, what was it, nitrogen and chlorine have the same electronegativity, even though they're different elements. So by these rules, I'd expect you to tell me they're polar covalent, even though actually that's wrong. But these rules work for the situations where you need to predict whether it's polar or not. And it's a heck of a lot easier than needing to go look up electronegativity values and look at the differences. Okay, so just using these ideas, a bond between iodine and iodine, what kind of a bond is that? Yeah, we have the same two atoms, right? So that's going to be a nonpolar covalent bond. How about cesium and bromine? Ionic. Kind of have to, check out the periodic table because you always want to know, is it a metal or a nonmetal? This is a metal, so this is an ionic bond. How about phosphorus and oxygen? We should predict that that's polar covalent because those guys are different, right? And so the chances are really good that their electronegativities are not the same. Any questions?